Bismillahirrahmanirrahim. Chapter 36, entitled as Wave Optics. Right. In previous chapter, chapter 35, we have studied light rays passing through a lens or reflecting from a mirror to describe the formation of image, if you still remember. Right, this discussion with the chapter 36, okay, and also chapter 37 later on, going to complete our study of the ray optics. Okay, we are going to concern with wave optics, also sometimes known as physical optic. Okay, what is physical optics or wave optics? It's actually the study of interference, diffractions, and polarization of lights. So if you see this diagram, the bird here, very beautiful, lots of different color for every single part of the bird. If you see this bird at different angle, you will see different colors, right? At this part, for example. This must be somehow due to the reflections and refractions of the light ray. Alright, let's begin our investigation. The first one is about Young double-slit experiment. Okay, before we begin with the details of the Young double-slit experiment, let's recall that we have learned in chapter 17 that wave in interference model and found that superposition of two mechanical waves can be constructive or destructive. Okay, that is for mechanical wave. Okay, for light wave, actually also interfere with one another. Fundamentally, all interference associated with light wave arises when the electromagnetic fields that constitute the individual wave combine. That is the main story how light wave can interfere each other. Interference in light wave from two sources was first demonstrated by Thomas Young. That is why we have Young double-slit experiment to be learned as our first step. Right. This is the schematic diagram of the apparatus Young used shown in figure here, A and B. This is the setting. This is the output of it. Okay, the image on the screen. Right. Plane light wave arrive at a barrier. This is the plane light wave. Okay, arrive at a barrier where we have two slits, S1, slit 1 and slit 2. Right. This is a barrier, okay. The long dimension of the slits is perpendicular to the pitch. Okay. The light rays from the two slits, okay, are in phase as they leave the slits. Okay. So, still remember how to have diffraction. When you have a bending here, means that the diffraction already happened. So, means that the size of the opening must be smaller compared to the wavelength of the incident wave here. Then the wave being diffracted, okay, coming out from slit 1 and also coming out from S2, also diffracted. And bear in mind that the wave that leaving S1 is in phase with the wave that leaving S2 because they actually originate from one single wave, the same wave. The light from S1 and S2 going to interfere each other and finally producing an image on the screen here. Okay, the image or the visible patterns of the bright and dark alternating, okay, upper part of the screen, lower part of the screen. Okay, this image called as fringes. When the light coming from S1 and S2 combine and meet at the screen here constructively, it's produce bright fringe. When the light coming from S1 and S2 combine, reach the screen and combine destructively, it's produce dark fringe. Okay, this is what happened on the screen location. We also called bright fringe as maximum, right? And dark fringe as the minimum. To have a bright and dark fringe, okay, we may refer to this diagram. This is figure 36.2. Okay, explaining about wave leave the slits and combine at the various point on the viewing screen, right? So all this figure is not up to the scale, it just conceptual, right? So let's say wave leaving S1 and S2 meet at point O, the center of the viewing screen, okay, whereby a crest of wave coming S1 meet crest as well, okay, S2, like wave coming from S2. So when crest meet crest, okay, what will happen? Constructive interference occurs at point O when the wave combine. Okay, so we will see bright fringe at the center of the viewing screen. Okay, again, now we are going to observe at point P. Okay, some distance from center of the screen. Okay, at point P, all right. Also going to see, we're going to observe constructive interference occurs at point P. Again, if crest meet crest or throw meet throw. Okay, for the wave that leaving S1 and S2. However, okay, we are going to observe some dark fringe whenever disruptive interference occurs at point R. Let's say, for example, when the two waves leaving S1 and S2 combine, because the lower wave falls 1/2 of wavelength behind the upper wave. What does that mean? Let's say this one is crest. However, the wave that leaving S2, when it reach point R in the condition of throw. Okay, so crest and throw, the difference between them, the length difference between them is 1/2, means half. 1/2 is a term. 1/2 means that half. Okay, half of wavelength. So when crest meet throw, they cancel out each other. That is why we are going to have disruptive interference. Consequent of it, we are going to observe dark fringe at position R. Okay, so this is on how, okay, this happen. So in terms of the difference, just now 1/2, okay, no different, okay, no path different. We call it path different. No path different. And this one, okay, path different, equivalent to order of lambda. Okay, so how we know this? Right, so if you see, okay, the difference between S1 and S2 is this one, which is equivalent to 1 lambda. Look at the shape of the lambda. Okay, so if we're talking about one complete wave, okay, so here is one complete wave, right? One complete wavelength. Then for this one, okay, if you do the arrangement, so this is lambda over 2. So path difference also can be symbolized as delta. Okay, which means equivalent to 0 in this case. For this case, path difference is equivalent to 1 lambda. For this case, path difference is equivalent to half lambda. Then it's going to produce dark fringe or destructive interference. Right? Okay, this is a must condition, okay, to have or to observe interference from two sources. The first one sources must be coherent. The sources of our wave must be coherent. What does that mean by coherent? It means that the wave must maintain a constant phase with respect to each other. Okay, so the phase must be the same. Right. Second part, okay, sources should be monochromatic. Okay. What does that mean by sources must be monochromatic? The wave coming from S1 and S2 just now, they should be of a single wavelength. The lambda of them must be the same. Okay, so these two conditions must be memorized. Okay, method to produce two coherent light sources. So if we refer to this diagram, this is actually the same diagram to our schematic diagram of our young double-slit experiment. So how we produce two coherent light sources from one single wave, okay, is incident on a barrier. Okay, where within this barrier we have two opening or slits. So means that, okay, whatever the wave that going coming out from S1 and S2 actually having the same wavelength because it's originate from the same wave. This is how we produce coherent, okay, light source that going to be interfere each other at this region and eventually producing fringes on the viewing screen. This is a must condition that Madam already mentioned just now. In young double-slit experiment, actually, you have to make sure that the wave or the lights emerge from the opening must be diffracted. Then it's going to interfere each other. If the size of the opening is equivalent to wavelength or bigger than the wavelength of the original wave, it won't be diffracted. It's going to pass through and they are not going to interfere each other. Okay, so what we want actually, the wave that passing through the opening S1 and S2 going to be diffracted. How to have this condition? So to have this condition, right, the size of the opening must be the size of the opening, let's say the D, okay, the D must be less than or equals to the wavelength. Then the diffraction pattern or the wave or the lights that passing through the S1 and S2 going to be diffracted. If the D is bigger than wavelength, okay, nothing going to be happen, no diffraction, and there is no interference, no image produces, no fringes on the viewing screen. Analysis model with in interference. So this is the one that Madam already discussed conceptually, how constructive and destructive interference pattern happen. Okay, whenever the path difference between wave that passing through or originate from S1 and S2 having no path difference, okay, we are going to have bright fringe at the center of the viewing screen. Whenever the path difference between these two waves is in terms of one wavelength, then you are going to have bright fringe again at point P. However, if the path difference between the two waves in the order of the half of wavelength, you are going to observe dark fringe, or it means that destructive interference happen. This is in terms of light wave. This is also actually can happen, okay, could happen for sound wave, right, as we discussed in previous topic. All right, so it's also about the path difference. Okay, so for those who would like to recall about this, please refer to previous lecture. Right, so we are going to do the analysis model in detail within interference. So based on this diagram, okay, this is the original wave, okay, and here is the S1 and S2. Here is separation distance, okay, between S1 and S2. All right, so this is the path taken. R1 for wave 1 that passing through S1. R2 is for S2 or a wave that passing through S2. Okay, so the difference between R1 and R2 is the delta or path difference. This is the path difference. So the path difference is equivalent to R2 minus R1, equivalent to D sine theta. Okay, how? Because based on this triangle, okay, the angle here, the theta here is actually the same to the theta within the yellow triangle here, right? That is how we manage to get path difference is equivalent to D sine theta. Right, for bright or constructive interference, D sine theta bright is equivalent to the order of the one wavelength, right? So lambda m, where m is the order, right? And the m is integer. It could be 0, positive, negative 1, positive, negative 3, 2, and 3, and so on. So when the m is equivalent to 0, it means that at the center of the viewing screen. When the m, the order is positive 1, means that the first order on the top, okay, to the top of the viewing screen. If it is negative 1, it means that the first order of bright fringe, okay, below or to the bottom part of the viewing screen, okay, and so on. For the destructive interference or dark fringe, D sine theta is equivalent to, so remember, order of half wavelength, right? So m plus half times lambda. Again, m is equivalent to 0 plus minus 1 plus minus 2. So for bright fringe, when we put m equivalent to 1, it's known also as central maxima. Okay, but for the dark fringe or destructive interference, when your m is equivalent to 0, it is known as first minimum, okay, or dark fringe. But for the bright, when it is m equivalent to 0, this is mean that center maxima, okay, or bright fringe. Okay, so for this one, this is going to be second order minimum. This is going to be third order minimum, and so on, because it shifted. If you still remember, this one, right? It shifted. At the center of the viewing screen is bright, and then it shifted. This is the m equivalent to 0. This is for bright, okay, m equivalent to 0. M equivalent to, this is for bright 1, positive 1, and here is m bright negative 1, and so on. For the dark, right, here is the dark, okay, where this is m equivalent to 0, dark. Okay, and here is m dark equivalent to positive 1. And here m dark equivalent to positive 2. Analysis model still wave in interference. So now we are going to observe the position, okay, on the viewing screen, where we symbolize it as y. Okay, let's say we examine at point P. As we know, triangle here, the big triangle here, the angle here, the theta here, must be the same to the triangle of the orange where the theta is here. Tangent theta for the orange triangle here is equivalent to y over L. L is the position of the viewing screen from the slits. At any position here, if it is about bright fringe, y bright is equivalent to L tangent theta bright. For the dark position on the viewing screen, y dark equivalent to L tangent theta dark. We know that path difference is equivalent to R2 minus R1 equivalent to D sin theta. Right. For D sin theta bright is equivalent to lambda m. Okay, with the condition of m equivalent to 0, plus minus 1, plus minus 2, and so on. So sin theta, okay, let's say for bright firstly, must be lambda m over d. Okay, if the theta is very small, tangent theta more or less to theta only, and sin theta more or less to theta only. Then you will have, okay, here going to be theta is equivalent to y over L. Right. Then you will have here theta is equivalent to lambda m over d. Then we're going to equate these two. Y over L is equivalent to lambda m over d. That is how we manage to get this kind. Rearrange this one. Y is equivalent to lambda m L over d, with condition that angle is small. Right. Goes the same for the position of the dark fringe. Okay. Just that the order must be plus half. Okay. Because it's in the order of half wavelength. So example 36.1. Measuring the wavelength of a light source. Right. A viewing screen is separated from a double slit by 4.8 meter. So L is given as 4.8. The distance between the two slits is 0.03 mm. So this is the slit separation distance D. Monochromatic light is directed towards the double slit. Okay, monochromatic. Okay, coherent source, alright. Okay, and forms an interference pattern on the screen. The first dark fringe is 4.5 centimeter from the center line of the on the screen. A, determine the wavelength of the lights. So, because condition given, information given to us is about dark fringe. Okay, first dark fringe at 4.5 cm from the center line. So given to us the y of the dark, right? So based on y over L is equivalent to lambda m plus half over d, right? So we are going to rearrange this. Our main interest is lambda. Okay, so lambda here is equivalent to y dark d over m plus half times L, right? every single thing must be in SI unit. Right? Then you will have this answer, or 562 nanometer of lambda. B. Calculate the distance between adjacent bright fringes. So, the distance between adjacent bright fringes must be ym plus 1, okay, the higher order, minus the lower order, y at m order. Okay, because on the viewing screen, okay, let's say this is the center, this is the slit. Okay, so this is the center of the viewing screen. So if let's say here we have y order m at this position, okay, from the center, and then let's say this is the next order. For this one, you are going to have ym plus half, okay, if they are next to another. So the distance between adjacent fringes, okay, must be ym plus 1 minus y order m. That is the distance between adjacent bright fringes. Alright. So from this idea, now, okay, substitute the ym plus half for bright fringe, okay, minus y at order m. Okay, so you will figure out that is equivalent to L lambda over T. Okay, substitute the rest of the information, you will get this amount, or 9 centimeter. This is the distance between adjacent, okay, adjacent bright fringe. Now example 36.2, separating double slit fringes of two wavelengths. A light source emits visible light of two wavelengths, lambda equivalent to 430 nanometer and lambda prime equivalent to 510 nanometer. The source is used in a double slit interference experiment in which L equivalent to 1.5 meter and D is equivalent to 0.025 millimeter. Find the separation distance between the third order bright fringes for the two wavelengths. So you have two different wavelengths. So it is asked about separation distance between the third order bright fringes of the two wavelengths. So actually you need to calculate one by one. The y for 430 nanometer, okay, and the y for 150 nanometer wavelength, okay, with the condition that m must be 3, right? Then you're going to figure out the difference between the y, okay, of 430 nanometer wavelength and 510 nanometer wavelength. So in terms of math, delta y is equivalent to y prime bright minus y bright. Okay, so this is a formula for the lambda prime, y prime. Okay, and this is a formula for the y bright. Okay, so since the L is the same, the M is the same, the D also the same, we can factorize it. So left with the difference between lambda prime and lambda. So if you substitute the rest of the information, this is the meaning or the answer. 1.44 centimeter is the difference or separation distance between third order of the bright fringe for two wavelengths. Okay, what if we examine the entire interference pattern due to the two wavelengths and look for overlapping fringes? Okay, are there any location on the screen where the bright fringe from the two wavelengths overlap exactly? Find such location by setting the location of any bright fringe due to lambda is equals to the lambda prime. So this is basically the idea, the y equivalent to y prime. because we want to take a look on the overlapping part, a position. Okay, so from here, okay, substitute the equation of y and equation of y prime with lambda m times L over d, right? So here we can simplify this because the L is the same, the D is the same, okay? So we will have, okay, m prime over m equivalent to lambda over lambda prime. If you substitute m prime and lambda prime here, you will have 43 ratio to 51. Okay, this is the m prime over m. So substitute the rest of the information. Okay. Cut the substitute part. So from here, okay, what does that mean? Okay, the 51st order of fringe, okay, of the 430 nanometer wavelength, okay, will overlap with the 43rd, okay, 43rd fringe of the 510 nanometer wavelength or light. This is the meaning. This is where, okay, the overlapping going to be happened. Okay, because we will put the condition of y equivalent to y prime. Okay, so for the 430, okay, it's the order of 51. Okay, and for the 510 nanometer of wavelength, the order of 43. So this order going to be overlap, right? So what is the y? Okay, so use one of it. Let's say we want to use 51. Okay, so remember the wavelength is 430 nanometer. So you use this equation, y equivalent to L, okay, m lambda over d. So you will get 1.32 meter. Why don't we calculate y prime? It's the same thing. Okay, you just make sure the order is correct with the wavelength. If you are using 43, you are going to use 410 nanometer of wavelength. You will get the same answer to this. So means that this is the position from the center of the screen to 1.32 meter is the position where, okay, the two fringes going to be overlap for two different wavelengths.